Hello, fifth graders. I hope you're ready for another exciting science lesson. So today we're going to do lesson 72, which is talking about weight as a force and how we measure weight. And so if you have your printout for your physics booklet, go ahead and get that out and you can highlight it, or you can look it up on your screen and read along as we go. So remember last time we talked about the four forces in nature. So the strongest force was strong nuclear force. Remember that. The second strongest force was electromagnetic force, which had to do with the electrons. Remember, the strong nuclear force is the protons and neutrons in the nucleus and what's binding them together. And then the electromagnetic force is the electrons and what's holding them into the atom. Okay, the third strongest force was weak nuclear force. Okay, that's what gives off radiation. It's the smaller particles inside, those little tiny ones inside the protons and neutrons. And then the fourth strongest is gravity or gravitational force. And that's the force that attracts objects to each other. Okay, so now we're on page 5, and we're going to talk about weight as a force. Okay, so I'm going to read paragraph 1. If you can follow along with me. It says the force exerted on an object by gravity is called weight. An object's weight depends on its mass and the strength of the gravitational force attracting the object. Although the mass of an object remains the same, its weight varies depending on its location. The less the gravitational force attracting an object, the less its weight will be. For example, an object at the top of a mountain has less weight than the same object at sea level because the gravitational force of Earth is less when the object is farther from the center of Earth. An object on the surface of the moon has less weight than the same object on the surface of Earth because the gravitational force of the moon is only about 1/6 the gravitational force of Earth. So I talked to you a little bit about that last time. So the mass is how much substance is inside matter, basically. It's how much matter you're made up of. But weight has to do with the gravitational pull on you as well. Okay, so at the end of the first sentence, I want you to highlight the word weight. Remember, that depends on its mass and the strength of the gravitational force. So after highlighting weight at the beginning of the first sentence, at the end of the first sentence, then you're going to highlight at the end of the second sentence, highlight depends on its mass and the strength of the gravitational force attracting the object. Okay, I'm going to repeat that. So at the end of the second sentence, highlight depends on its mass and the strength of the gravitational force attracting the object. Okay? So on Earth, the difference between the weight of an object at sea level and at the top of a mountain can be measured with instruments, sensitive instruments, or calculated mathematically, but the difference is too small to observe without an instrument. So you wouldn't be able to just put a scale at sea level and then put another scale at the top of a mountain and weigh two objects with the same mass. You won't see much of a difference that way. It has to be a very, very particular sensitive instrument to do that, if you wanted to try that out. Okay, paragraph 2. We're going to talk about the unit used to measure force and weight. So you're used to measuring your weight in pounds, right? But if you're talking about force and weight, like how much gravity is pulling on something, you're going to use something called a Newton. Okay, named after Isaac Newton, of course, right? So paragraph 2. The scientific unit used to measure force and weight is the Newton. The symbol for Newton is capital N. A spring scale, also called a spring balance, can be used to measure force and weight. Okay, so at the end of the first sentence, you're going to highlight the word Newton. And then above that word Newton, write a capital N with your pencil. Okay, so highlight Newton. in the first sentence and then write a capital N. That's what you're going to use to abbreviate it. Okay, and you use a spring scale to measure this. And I wish I had one to demonstrate with you right now, but I don't have them with me. They're also called a dynamometer. Okay, and we have these in our classroom, and we would have done an experiment with them if we would have been in the classroom. But basically, it's like this cylindrical tube. It's kind of a glass looking thing. It's really plastic, but you can get a glass one too. And it's got a little hook at the bottom. And so the top part kind of looks like a graduated cylinder. It's got these lines of measurement on them, and they're measured in newtons. And you put something on the hook at the bottom, and it'll pull it down and show how many newtons it is. Okay, so in our experiment, we would have tested out different things and measured how many newtons it is. But you just put something on a hook, and it'll pull it down, and it'll show you how many newtons. So it's kind of cool to try out. Okay, and that's called spring balance, or it's called a dynamometer. So paragraph 3, we're going to talk about how to find weight in newtons. The force of the Earth's gravity on an object depends on the mass of the object. On the surface of Earth, an object with a mass of 1 kilogram, that's the metric unit of weight instead of pounds like we use, it has a weight of about 10 newtons. So for a mass of 1 kilogram, you have 10 newtons. It's basically just adding a 0 to it for newtons. An object with a mass of 100 grams, so keep in mind 1 kilogram is 1,000 grams. Okay, 100 grams, which would be less, has a weight of 1 newton. Okay, so it's all about that place value. Okay. So 1 newton is equal to the amount of force needed to accelerate an object with a mass of 1 kilogram, 1 meter per second per second. In other words, 1 newton of force will move 1 kilogram, 1 meter in the first second, 2 meters in the next second, 3 meters in the third second, and so on. Okay, so if I had a 1 kilogram block and put it right here, if I had 1 newton of force, it would move that kilogram block 1 meter in 1 second. That's how strong that force is. Okay, and 1 kilogram is, comparable to a pound. It's not exactly, but a kilogram is comparable to a pound. Okay, so 1 kilogram is 10 newtons. Okay, so if we had 3 kilograms, it would be 30 newtons. You just add a 0 for your kilograms. Okay, but it's not exact. So this is the closest approximation is 9.81 newtons. We just rounded up to 10. Okay, so if you want to, you can write 9.81 above 10 newtons if you want the exact amount. Okay, and then there's also a photo of a spring scale on that Nancy Larson website. So if you want to log into that website with the username and password that I gave you, you can see a picture of what a spring scale looks like. I'm going to try to find a picture to post on the website on Google Classroom as well. Okay. So the diagram at the bottom left on page 5 in your booklet shows the 2 scales on the spring scale. Okay. So to measure force and weight, you're going to use the scale on the left because they're measured in newtons. Okay. So 1/10 of a newton on the scale is going to be 1 line below 0. I know it's kind of complicated for me to picture this right now without the spring scale in my hand. Okay, so 8/10 of a newton on the scale would be 3 lines below 5/10. So it's 5, 6, 7, 8. 3 of them below. Okay. Let's see. So it says use your red colored pencil. You can use a colored pencil or just look at the diagram because I know if you're doing it digitally, you're not going to have a pencil to mark on. But you are going to show 8/10 of a newton on the scale that shows 8/10 of a newton. So you just shade it in. And then the scale on the right tells us the mass of an object, which would be in grams. So each line on that spring scale represents 10 grams. Okay, the spring scale is numbered by 50s, and there's 5 spaces between each one, so it's going up by 10s. That's what it's saying. Okay, so if an object on Earth has a weight of 8/10 of a Newton, what would its mass be? So it's going to go up 2 spaces. Okay, it's kind of like percentage when we were talking about percents, when you move it over 2 spaces to the right. So if it's 8/10 of a Newton, you move it over 2 spaces to the right to show how many grams, which would be, move your decimal place 2 spaces to the right, it would be 80 grams. Okay? So this is kind of complicated without me showing you, but you can kind of see by the picture in your booklet. Okay, and like I said, to use a spring scale, you just put something on the hook at the bottom, and it will pull it down and show you the measurement. And we would have done an experiment with that to show you, but I can't do that with you right now. So we'll just pretend, and I'll see if I can find a video of them using a spring scale to give you an idea of what that would look like. Okay, so when it's a heavy object, it's going to pull harder, and the spring would come even further down. If it's a really light object, it just comes down a little bit. Okay, and we're going to skip the chart that it shows you. And basically, that's about it for weight. Okay, so you can rewatch this before you do the lesson review if you want. And you can use your booklet if you want to keep that with you as you're doing the lesson review 72. Or you can, if you have the digital document, you can keep that open and look it over as you're completing lesson 72 because it's just a review. So I'm going to post that on Google Classroom and then you'll be all set. All right, we'll see you next time.